Swayam Prabha. Digital India. Educated India.
So, today we will see microstructures of structures, and it is in continuation with what we had discussed last time. Last time we saw a number of structural properties of the material, different structural uses of the material. Under different conditions, the material is supposed to have strength. Now we should start the investigation on what is the source of strength, from where does the strength come from. Because if you look at a structure which withstands heat, for example, from where does the strength under high temperature comes? If you have a structure that is tough even at low temperatures, then we need to find out at low temperatures what brings in the toughness. So basically these are certain aspects of strength: toughness, hardness, the Young's modulus. So these are certain aspects of strength which have certain source, and these sources can be identified only microscopically, and that is the reason why we are now going to delve deeper into the different sources of strength. So let's begin with the periodic table, which has got a number of elements, and by now every element has found use in practical application. So even if some of the elements are available in smaller quantities, few others are available in large quantities, still each of the elements has got some practical use, and some of the structural uses are commonly found for iron, nickel, titanium, aluminum. So we do have, or we do use products which require a structural strength coming from these materials. So these are most commonly used materials. Compared to that, you would have tungsten or hafnium, tantalum. These materials are relatively exotic, and they are not used unless their properties are warranted by the application. But on a normal scale, we use typically chromium, manganese, iron, copper, zinc, aluminum, silicon, carbon. They are more of functional materials, although carbon can also be used for structural applications, lead. So these are some of the structural materials which have strength under different conditions. So these are used as metals, and even better used as alloys. Compare with helium, neon, argon, krypton, xenon. These are functional materials where purity is very important. In these elements, like all gases, for example, purity is extremely important. So gold, which is another functional material, platinum, silver, here we are looking for purity. Normally purity is the one that is most important. But when you talk about strength, one specific element does not have strength under all conditions of functioning. For example, you might have diverse working conditions, and one element will not be able to stand up to all of them. So that is the reason why we need what is called as alloying. But before we talk about alloying, there is one point I would like to bring out, is that for all common materials, we have just one atomic weight. You don't have isotopes like iron, copper, aluminum. You don't have isotopes of these materials, but there are a number of materials where there are isotopes, and so if we have to quote one single value of that of the structural strength or atomic weight or whatever. So to calculate the atomic weight, for instance, we have 4 different let us say naturally occurring isotopes, and if we have to quote one single value, then we would have a linear addition of the percentages. So, we have the weighting factor which is the percentage of the that particular isotope and the atomic weight of that isotope, percentage of isotope and atomic weight here. So, for all 4 we add them together linearly, and then we get the single average atomic weight of 140.115. So, when we quote an atomic weight for a number of elements, it is an average atomic weight considering different isotopes. Now, these are these materials are required and as alloying elements in many of the to form many alloys, to impart certain properties to the base metal. So, although cerium itself might not be an individual structural material, it gets added into many of the elements to impart its properties, impart good mechanical properties to it, and therefore this alloy and alloy formation therefore is useful in combining the good properties of many elements, bringing them together and then cooking up a material that withstands a big variety of trying conditions. So, we know that structural materials are about strength. So, we have elasticity, which means that under small loads the material deforms very little, and when the load is released, the deformation no longer remains behind, it gets retrieved completely. So, the material comes back to its original shape. For example, if you compress a spring and then release it, the spring will come back to its original position, that is called as elasticity. Compared to that, plasticity is something where the material remains in its deformed state. So, if I want something to get to reduce in height by let us say 10 millimeters, and then it does not stay in a reduced condition, I apply sufficiently light load so that on release of load the height gets restored to its original height, then I would say it is elastic deformation. My objective of compressing it by 10 millimeters has not been achieved, because all deformation has been retrieved as in case of elastic deformation. So, I have to cross a certain load. So, I have to go on loading the material. So, load cannot be light, it has to be sufficiently heavy. I cross one particular value of load so that the permanent deformation sets in. So, what it means is that the loads required for permanent deformation are much higher than the loads required for elastic deformation, which can be retrieved, or which can be which becomes 0. The deformation comes back to, the sample retrieves its original dimension after the release of load. So, that is elastic. In case of plastic deformation, the shape, the change of shape remains permanent. So, if I have applied sufficiently high load, so that it crosses a limit called as the yield point. So, it crosses a limit called as yield point, then whatever deformation you might have given it remains permanent, and it is not retrievable. So, we have elasticity and plasticity as far as our common experience goes. So, you bend something, it comes back, it does not come back to its original position fully, but it tries to come back to its original position, that we call as spring back. What is that? That is because of elasticity getting retrieved. So, you bend it by some 40 degrees angle, after removal of load it comes to 35 degrees. So, what does it mean? Those 5 degrees are the the retrieval of those 5 degrees is because of elasticity. In spite of recovering, in spite of removing the load, the material continues to remain bent at 35 degrees, means that there is a permanent deformation taking place, and that is the result of plasticity. Now, to what extent can you deform it? To what extent can you deform things permanently? So, can you change the shape to a large extent permanently? Then it is then that would mean it has got high ductility. So, materials like steel, aluminum, copper, gold, so these are materials which have got extremely high ductility because they are capable of changing their shape to a large extent, and that is the reason why so many items like wires, for example, are made from copper and aluminum because they are extremely ductile. Steel, you have wires being made from steel which are used for our lifts. So, the wire ropes which are used for heavy duty load lifting are made by imparting extremely large amount of load, extremely large amount of permanent change in shape, so that the final shape of a thin wire is obtained and it remains as it remains in a deformed condition, meaning in the final shape of a thin wire. So, the extent of ductility, plasticity refers to ductility, and malleability is also related with ductility, and we see aluminum foils, copper foils, gold foils, etc. being made, and that is the result of malleability. So, you can make a foil, you can make flat products of a very thin size, let us say 5 microns, 10 microns. You have these silver foils on sweets, extremely thin foils made of silver. Why is it possible? It is possible because of very high level of malleability that silver has. The ductility of silver is extremely high, and that is why the malleability of silver makes it possible for us to make very thin foils which can go as decoration on the sweets. Compared to that, stiffness is related with elasticity. So, I gave you the example of a spring. So, when the spring is pressed, when a spring is compressed or extended, it comes back to its original shape after the load is removed. But if you take a spring that is compressible or extendable using very light load, as opposed to a spring that can be compressed or extended using a very high load, one spring is less stiff as compared to the other. So, what we mean by stiffness is load per unit deformation. So, that is what we call as stiffness. So, both the springs will recover their deformation, both the springs will come back to their original position after the load is released. But the load that is required to deform the spring in an elastic manner will be higher when the spring is stiff as compared to when the spring is not stiff, meaning when it is kind of compliant or less stiff. So, the stiffness is a very important part, particularly when you talk about machine structures. Stiffness plays a very important role as a structural material. Stiffer is a machine, better is the behavior of the machine, greater is the accuracy of products which you make from the machine. So, basically stiffness plays a very important part in structures, and for higher stiffness, stiff structural materials will have to be used in order to make the structure stiff. Brittleness is related with ductility. It is essentially lack of ductility. So, ductility, I have already told you, enables you to deform the material to a great extent, whereas brittleness is just the opposite of it. It means that the material does not get deformed at all. So, basically the material gets deformed only in the elastic manner, very small strains, the elastic deformation is retrievable, but there being no ductility, the material just fractures. So, it is either integral during elastic range of deformation, and it will fracture into pieces and have no ductility at all. And so, there is the condition of being in a deformed state does not exist. So, when the material is brittle, as in case of cast iron or glass, right, we have experienced a glass object shattering into pieces. That is because it does not have it does not have any ductility at all. It fractures very easily. So, when you break glass, you make a scratch on the glass and then just bend it, and the glass breaks. So, small scratch results in breakage of the glass because it has no ductility. So, a small strain that is applied to it just breaks it. So, this is what happens when you deal with brittle materials. Hardness is a property which again refers to, or it is related with the load that is required to change the state from elastic to plastic deformation. So, hardness is something that, simply put, is the ability of one material to scratch the other. So, hard glass, hard diamond scratches any metal. The diamond can scratch even glass for that matter. So, you take a diamond tool and scratch glass and then use it for breaking the glass, so glass cutting to specific shapes and for making lots of pieces of art is done by making a scratch of that particular contour and then just bending it and then separating the two pieces along that contour. So, the glass is easy to break, and therefore, if you make a scratch along a particular line, it is very simple to break it along that line. So, that is because there is brittleness in the glass. Now, usually brittle materials are hard as well. The usual diamond is something that is extremely hard and it scratches almost any material. Glass will scratch steel, copper. Steel scratches aluminum and copper. So, whether material is hard or soft depends on what scratches, which material scratches the other. So, hardness is a property that is an important property when it comes to wear resistance, meaning where the rate of wear and tear of a hard product is extremely small as compared to a relatively soft product. So, the wear and tear is much lower for hardness, for material which is harder on the surface, and that is why you have many surface hardening procedures. So, to give strength to the material on the surface. Let us say you take a gear for example. So, two gears are meshed with each other, they have to transmit lot of torque, they have to transmit motion, and these two gears are undergo rubbing with each other at a very high load. So, now the wear on these rubbing surfaces will result in enormous amount of wear if the surfaces are sufficiently soft. If they are hard, if the surfaces are hardened, then the resistance to abrasion, the resistance to getting scratched, the resistance to wear will improve with an increase in the hardness. So, how hard a surface is determines its wear resistance. Toughness is related with ductility and strength both, because it is the energy that is required for permanently deforming a particular material. So, if you have a ductile material which is extremely ductile and it can be deformed very easily, then it is not tough because it does not absorb sufficiently large energy, that is because it does not have sufficiently large amount of strength. It has got ductility, it is capable of taking lot of deformation, permanent deformation, plastic deformation, but it is not very tough because it does not have too much strength, it does not require too much of load for the deformation. On the other hand, a material would be extremely tough if it has strength as well as ductility. So, it has got lot of energy that is absorbed by the material as it deforms in a plastic manner to a permanent shape. So, these are some of the properties which we will always talk about when we talk about structural materials, and this is what we have done in the last class. So, now I will come to what I was mentioning earlier. None of the metals are used as single metals. So, you need to alloy them to enhance their properties, because when you have service conditions, they are not just about strength at a particular temperature. You have a big variety of service conditions which need to be satisfied simultaneously, due to which a single material might not be able to stand up to all those conditions, and that is the reason why we we alloy carbon with iron, for example. When we alloy carbon with iron, the strength goes up quite significantly, and therefore the weight of the product that comes, that results for the same strength is much lower than what would have been the case when it were made from iron, only iron, right? In fact, during the railway mania in England, earlier the rails were used to be made using only iron. But later on, when steel was invented, when steel metallurgy was researched and it became a practice to make rails using steels, the rails were much lighter, much stronger, and much more durable, as a result of which the manufacturers who restricted themselves to making them from iron went out of business. So, steel is far superior in terms of properties as compared to just iron. So, that is the reason why carbon is alloyed to with iron to different extents to manufacture different grades of steel. So, whether it is our vehicles like car, rickshaw, bus, trains, so all these, the bodies of these are made from either steel or aluminum. That is because an aluminum does not mean it is just pure aluminum, it is aluminum alloy. For example, copper is added to aluminum. Copper is added to aluminum, and fuselage of the aircraft is made from these aluminum copper alloys. So, these addition of copper enhances the strength of aluminum because strength to weight ratio is very crucial in aerospace industry. So, if the strength increases significantly by addition of an alloying element, plus there is some improvement of properties as well, other properties like degradation related, then the performance of that particular material, structural material, gets enhanced tremendously. We have aluminum magnesium alloys being used for auto bodies, or basically bodies of the vehicles, skin panels as it is called. These are expensive because aluminum is expensive, but then these are much lighter as well as compared to steel. So, if you want to make a very lightweight vehicle which will consume much less oil, much less fuel, highly fuel efficient vehicles, in that case one would use aluminum magnesium alloys, and these have been used very successfully in many of these commercial vehicles produced. Aluminum copper magnesium similarly, so you are basically trying to combine the goodness of different materials. For example, aluminum has got a density of 2.7 gram per cc, copper has got a much higher density, close to 8 gram per cc, whereas magnesium has got a density of 1.7 gram per cc. So, now what you are doing is by replacing aluminum with magnesium, for example, so by adding certain amount of magnesium, you are making the alloy much lighter. So, if you make aluminum lithium alloys, lithium has got a much lower atomic weight as compared to even magnesium. So, naturally you are trying to reduce the weight of the alloy that is being used, plus increasing the strength. So, the strength to weight ratio increases, plus you are taking the advantage of a reduced density of the resulting alloy. So, now the benefit is twofold. One is, to start with, you do not need a great volume of the material to do the same job, to withstand the same load. So, the relatively smaller volume of material is able to withstand that much of structural load, plus because of the lower density, the mass, the weight of the material that is required gets reduced, because first thing is your volume is reduced, and furthermore you have used material of lower density. So, you have double benefit by adding materials of elements of lower density to elements like aluminum. You have a few other things like titanium, aluminum and vanadium. So, these are again added for very specific purposes. We will see the purpose of adding each of these, but then the whole idea here is to enhance the strength for a given weight, or enhance the strength and reduce the weight. So, attack the problem from both the sides, and then achieve significant weight reduction and significant savings in terms of fuel. We know stainless steels iron, chromium, nickel. So now only iron can get corroded, only iron can get oxidized. You find oxide scales forming on iron articles. The durability is very low, degradation is faster. But then when chromium and nickel are added, you get what is called as 18-8 stainless steel, which we use for utensils at home. And these utensils last for years together without any degradation, something that wouldn't have been possible if only iron were to be used. So it's very important that the properties of chromium and nickel get imparted to iron or get added to the goodness of iron, and the strength of the material goes up, and the properties of a variety of properties under different service conditions, a variety of service conditions get enhanced by the presence of these alloying elements. So what we are saying is that every alloying element is intentionally added. What you are doing is, you want the goodness of that particular element to work towards enhancing the property of the host element. So in iron carbon, iron is the host element, aluminum copper, aluminum is the host element, aluminum magnesium alloy, aluminum is the host element, iron chromium nickel, iron is the host element, titanium aluminum vanadium, titanium is the host element. So this way the properties of the host element gets enhanced significantly by the intentionally added elements like nickel and chromium in iron, or carbon in iron, copper in aluminum, magnesium in aluminum, and so on. However, the picture is not so rosy, because there are many other elements which are present without our intention of adding them. So these are elements which you would like to remove. You can do without them, but unfortunately it is impossible to remove all of them. So such elements which remain behind in spite of all the best effort you might make is called as impurity. I mentioned to you about gases being required in a pure form, but gases also have certain amount of impurity, and that is the reason why gases are available as 99.9% pure, 99.99% pure, 99.999% pure, but again it is never 100% pure. So even a small amount of impurity, particularly with gases which are essentially functional materials, impacts the processing of materials, the manufacturing of the products to a great extent, because the small amount of impurities are extremely damaging for many applications. So it's very important that the impurities are reduced to a minimum for critical applications. For instance, iron has phosphorus and sulfur as two major impurities which are present, and these impurities, it's impossible to get rid of them completely. So what you need to do is minimize them to a level where they are rendered harmless. So you can add certain alloying elements to take care of these harmful elements so that they are rendered harmless. So everything is not added in order to enhance the properties. So the properties of the host material get enhanced indirectly, because some of the elements handle the deleterious effects of many impurities. For example, manganese is also added to iron. So if you take iron and carbon, additionally you add manganese, the sulfur which is present as an impurity gets fixed, meaning it reacts with manganese, becoming manganese sulfide, and then the effects of sulfur being present are not deleterious effects of sulfur being present are reduced. They are not completely avoided, because what happens is this manganese sulfide also is something that that is less of a nuisance, but then yes, it also reduces the properties of the material. But then if you control the morphology of the manganese sulfide, then it is possible to minimize the damaging effects of sulfur as well as manganese sulfide. So what I am saying is that alloying elements enhance the properties while impurities degrade the properties. So many times people use alloying elements or address alloying elements as impurities, which is wrong, because alloying elements are intentionally added, impurities are not, they are unfortunately present when you would like to do without them. So, the source of strength in this macroscopically visible part. So, this is an engine block which has got a large number of atoms present here, and they are the ones which are imparting the strength to it. So, the source of strength is not on a macro, I mean the strength is seen in macroscopic scale. In an engine block, what you need is sufficient degree of structural strength at high temperatures. It should have sufficient corrosion resistance, because you have fuel being burned and there are gases generated as a result of the combustion. So, that they can be corrosive in nature. Then you have humidity, and then there are host of other service conditions due to which you need the structure to be strong enough under room temperature, low temperature, high temperature conditions, as well as under some degree of corrosive environment. Now, all these capabilities are imparted to this, not I mean they do not come all of a sudden, they have sources at atomic scale, so at atomic level. So, you have some atomic scale structures which get aggregated into some nanostructures having certain properties, and these nanostructures impart their goodness to microstructures, and these microstructures finally impart the goodness to the final macroscopically visible structure. So, one has to start with the atomic scale effects, because that is where the sources of strength lie. So, if you tweak something here, you are going to see the effect there. If you tweak something here, you will again see either good or bad effects depending on how you have tweaked, and so the effect here will be felt as a result of a change here, because this change will go through a number of processing routes. So, this change will get compounded, or this change will take place with every processing step, and finally you end up with this kind of shape over here. So, we have a material which is an aggregate of many atoms, which is processed at certain temperature, certain pressure, right, under certain environment which is called an atmosphere. So, if you have if you are heating it in an oven, and then you have not air but just nitrogen around it, it is nitrogen atmosphere. If you have argon, if you have neon around it, you have that particular atmosphere. So, this way you have either inert, active or inactive atmosphere when you are processing the material, and some materials do require this atmosphere. For example, magnesium, which is used in our sparklers and our crackers, has extremely high affinity for oxygen. So, if you melt magnesium and then try to pour it, it can explode, because it has got extremely high affinity to oxygen, and therefore, you need to keep oxygen away from magnesium when it is being poured, particularly because it is extremely reactive under those conditions. So, now you need an atmosphere, you need to create an envelope of some other gas which would cut out the oxygen and prevent any contact of oxygen with that particular material, molten magnesium for example. Similarly, when you do the welding, when you do welding of even steels, what you need to take care of is no oxygen should come in, because during welding, arc welding particularly, you melt the material and that can get oxidized if there is a oxygen envelope around. So, you need to take care that there is some sort of shielding gas or some sort of atmosphere which is locally generated, which keeps out oxygen and lets only those gases which do not react with iron come in contact with iron when it is molten in particular. When it becomes relatively cooler, when iron is solid and cool, when it does not react with oxygen, it can get exposed to oxygen without any difficulty, without any adverse effects. But then so processing does modify the structure of the material. So, the structure results from processing, and this structure leads to different properties, and properties lead to performance. So, on the left hand side of processing, you have the aggregate of atoms, and these atoms, this aggregate of atoms, which we call as material. So, these atoms could be of different species, it could be a mixture of different metallic elements, and this chunk of atoms of different metallic elements put together will be processed into a different structure, and that structure will generate properties and properties to performance. For example, now here for these three, so here this one is transparent, this one is translucent, and this one is opaque. Material is the same. So, the properties, I mean the chemical composition is the same. So, but the processing is different. So, if you look at the left hand side of processing, the species of atoms which are being processed, they are the same, but the way they have been processed to, let us say, amorphous condition in this case, semi-crystalline condition in this case, and completely crystalline state in this figures. Therefore, the properties are different. The structure here is amorphous, structure is semi-crystalline, here it is fully crystalline. So, the structure has in these three cases is due to the processing conditions. So, to get this and that, you do not have a single processing condition. You need three different processing conditions to get this structure as different from this, as different from that. So, each processing route leads to a different structure, and naturally that structure would lead to different properties. So, here the transparency is very high, here transparency is nil because of different structures imparting the different degrees of transparency, and therefore the performance naturally will get affected, because if you want to cut out light, its performance would be brilliant, but if you want to read something through this or make a lens out of it, or an optical in the optical part where transmission of light is important, you would so this will perform the best. So, if you look at the sources of strength, it is in case of metals particularly, you have the interatomic bonding and the molecular structure, as we call it, imparting the properties. So, the strength is finally the outcome, and that is required for required performance. So, to get the strength, so as we have seen here, the strength is designated by a number of properties which we saw earlier, and the structure that is formed is as a result of the arrangement of atoms in a specific way, and the interatomic bonding that keeps them together is something that is the source of strength. So, if this bonding were not there, they would just atoms would get just scattered and would not remain in position, but then what keeps them in position is the metallic bond over here. Similarly, you have a covalent bond, particularly in polymers you have covalent bonds between carbon and hydrogen, and then these polymer chains, they are long polymer chains, and then they get entangled with each other, or they get wound into different configurations. So, these are long chains, and so the strength is generated through covalent bonds, which are basically with carbon and hydrogen in case of polymers. Similarly, you have van der Waals bonding, hydrogen bond, which are relatively weak bonds, and they do not impart too much of structural strength. So, we will not consider them with too much of seriousness, but then what is important for us here is the metallic bond in most metals, covalent bond particularly in polymers, and the ionic bond, which is typical of ceramics. We will see ionic bond a little later. So, the metallic bond is typical with metals, in which we have an ion core, and there is sea of valence electrons. So, there is basically an electron cloud or sea of valence electrons, which are like a pool of electrons which are present there. We have ionic bond as a bond resulting from two ions, as sodium and chlorine, and there are two forces, one of attraction, other one of repulsion, and wherever they get balanced, the spacing between the two ions gets decided by the relative forces between the two. So you have sodium ion attracting chlorine ion. It's a highly electropositive element. The chlorine is a highly electronegative element, and therefore the bond strength is going to be extremely high. So the attraction is as a result of the charge on each electron, number of valence electrons, and then it is inversely proportional to the separation, interatomic separation. Whereas the repulsive energy varies non-linearly, and therefore it is proportional again inversely proportional to nth power of the distance of separation. So if you look at the ionic bond, you have sodium chloride and magnesium oxide having ionic bonds, for example, because they are products of highly electropositive elements with highly electronegative elements. And so the corresponding strength is of the order of 1000 kilojoule per mole, 640 kilojoule per mole. Very high bond energy is involved in case of ionic bond. Now here you have two electrons involved creating the bond, to create the bond. So magnesium has got valency of 2 and oxygen has got valency of -2, and therefore you have MgO as a compound which melts at a much higher bonding energy, which has got very high bonding energy, and corresponding melting point is also that much higher. So sodium chloride has got one single electron being exchanged. So you have so sodium gives one electron to chlorine. So 640 kilojoule per mole is relatively lower energy as compared to magnesium oxide, and the corresponding melting temperature is also relatively lower. Covalent bonds are they can be extremely strong, or so covalent bond, for example, is as in diamond, has got very high energy, and the corresponding melting point is very high, whereas carbon in graphite will have a much different bonding energy. So it all depends on how the atoms are arranged, how the ions are arranged. So particularly when you have metallic bond, you have the bond strengths deciding the melting points here, and the corresponding energy that is needed to break these bonds. So mercury, which is liquid at room temperature, has got an extremely small bond energy, whereas tungsten very high bond energy and correspondingly high melting point. Gases typically are bound by van der Waals forces, which are extremely weak, and that is why you don't have any specific structure of atoms. Atoms are not arranged in a specific array or specific sequence or specific pattern in gases. It's a Brownian motion or a random motion of these atoms, and therefore that is because of van der Waals forces. Nevertheless, the atoms are maintained together, as atoms are brought together by the van der Waals forces, and the gas also is the atoms are kept maintained together. Hydrogen bonds are typically involved where hydrogen is present, so ammonia and water are good examples of that. And again, bond strength and bond energy basically and the melting temperatures are easily correlated. So if you look at the two energies and the corresponding forces that are generated, if you look at the energy of attraction and energy of repulsion, so you have the repulsive energy decreasing with interatomic separation, and similarly attractive energy of attraction also gets close to zero, or so it falls like this way, and then the overall energy, the sum total of the energy takes this shape, which is shown by a full line. So this is the depth of the energy well. This is the depth of the energy well, which is related with the bond strength. So higher is the depth of the energy well, stronger is the bond, and therefore you have a greater melting point, deeper is the energy well. So the point of minimum energy, is the position where the atom will be in the most stable condition, and that will govern the interatomic separation. So, this particular interatomic separation is able to maintain the atom at its minimum energy level, and at that particular level the force acting on that atom is also 0. So, at 0 force the atom will naturally remain stable. Anything more than that, it will tend to go away from its stable position where 0 force was acting. So, it will get pulled in the direction of the force, and when the force is released it will come back to its original position. So, if the atom is pulled this way, it will get deformed in that position because you have supplied some energy, you have pulled the atom using a certain force, but then if you remove the force, the atom will come back to its original position because it will achieve its minimum energy level at 0 force. So, this leads to what is called as elastic deformation. When we say elastic deformation, it means that the atoms will come back to their original position, which is so called mean position, and once the load is released, the atom will get back to its original position and remain stable there. However, if you apply sufficiently large force so that it goes over the energy barrier, or if you give more energy like that, and then it will go down the energy barrier to another stable position at a much higher. So, what it means is that once you apply sufficiently large force, you are essentially displacing the atom from one stable position to another stable position. So, here this R naught is the initial stable position, and you can displace it to another by another R naught, but then the energy required will have to be it will be go up an energy hill and then come down again to practically 0 energy at the next stable position. So, this way you can move the atoms permanently by applying a sufficiently large force, and that will be seen as plastic deformation. Whereas, when I was talking about elastic deformation, it is small movement of atom about its mean position, so that the atom comes back to its mean position once the load is removed, and that is responsible for the elasticity or elastic behavior of the material. So, if you take an example of this potassium bromide K plus and Br minus, so what we are supposed to do is to find out the separation distance when the ionic radii are given. So, here the force of attraction is the derivative of dEA upon dr as so what we see here is the same thing. So, at the bottommost tip the derivative is 0 and the corresponding force is 0 over here, and that is why the atom is in the most stable condition over here. Whereas, at other positions depending on the slope you will get the corresponding force. So, it will be a non-zero force at any other location. So, if you take EA for energy of attraction to be minus A by R, then you have the force equal to A upon R square, and the value of A is given as this Z1 into this. You have a monovalent ion. So, potassium has got valency 1, bromine has got valency minus 1. So, only one electron is exchanged, and therefore, this product gives you the force of attraction to be so small. And then if we assume that the position of stability of every ion is such that the two ions just touch each other, okay, they just touch each other, then R naught is equal to potassium plus ionic radii of the two, and then therefore, this is the R naught, which is the position of stability for a given atom, for a given ion. Okay. So, now if you take the force of attraction at this small distance, it is a very small force of attraction. and since the force of attraction equal to force of repulsion in its most stable condition, you would have this as the force of repulsion as well. So, force of attraction and repulsion are one against the other. So, for one bond, such a small force is acting. Now, in a very small piece, let us say if you have 63 grams of copper, for example, you have Avogadro number of atoms in it, roughly Avogadro number of atoms. So, 10 to the power 23 atoms. Now, these are going to be bonded with a similarly small force, but then when these are bonded together with so many neighboring atoms, then the strength of the aggregate becomes quite significant, that the strength of the aggregate becomes extremely large. So, that is how our macroscopically observed strength is a combination is attributed to the strengths of individual bonds, which are by the millions, by several millions of bonds inside the chunk of metal which we use macroscopically. So, that is how we see the strength as a result of this multiplicity of very small strengths of each individual bond. So, when we talk about an ionic bond, all ionic bonds are not of 100% ionic character. What it means is that different elements of different electronegativities come together, like silicon and carbon, very small difference in electronegativity, but they form silicon carbide. You have sodium chloride with two different very largely differing electronegativities. So, sodium highly electropositive, chlorine highly electronegative, they come together and form a strong bond. Carbon and hydrogen come together. So, the degree of ionicity, the extent of ionicity in this bond differs depending on the electronegativities. So, lower is the difference in the electronegativity, lower will be the ionicity. Large is the difference in the electronegativity, like magnesium and oxygen, for example, you would have a ionic bond, meaning a very high degree of ionicity. So, here the ionicity is given by this expression. So, the expression was also given in the previous slide over here. So, here the percentage of ionicity is, so this is square actually, this should be at the top here, and so these are the X and XB are the electronegativities of respective elements. So, now if you look at the periodic table involving these electronegativities, you have carbon 2.5 and silicon 1.8. So, there is a very small difference in the electronegativities as opposed to, let us say, oxygen 3.5 and magnesium 1.2. So, there is a significant difference in the electronegativities here as compared to silicon and carbon. So, naturally the magnesium oxide will have much higher ionicity as compared to a silicon carbide bond. Similarly, if you take carbon and hydrogen atomic bond, which is found in hydrocarbons and plastics, polymers for that matter, then you have just 3.9% ionicity, which means that the bond is primarily covalent. So, it is 96% covalent, means it's we practically regard it as covalent bond. So, now there are many other precipitates which are interatomic materials, interatomic or intermetallic particles which are formed as a result of copper and aluminum reacting with each other, nickel and aluminum, nickel and titanium. So, depending on these electronegativities, the strength of these particles will differ, the bond strengths will differ, and therefore, the degree of ionicity will also differ depending on the electronegativity. So, difference in the electronegativities is the source of strength for these particular particles. So, the source of strength being the difference in electronegativities, all particles are not going to be of equal strength, all particles will not have the same degree of ionicity in their bonds. So, I would leave it to you to calculate the degree of ionicity for these different intermetallic compounds which are found in many structural materials of consequence. So, typically the degree of ionicity is given. So, some of the calculations have, some of the results are already given in this table. So you can check based on your calculation whether you are getting the right outcome, you are getting the right result, whether you are using the formula properly, and then based on that you can go on to calculate the degree of ionicity for so many other intermetallics. Aluminum oxide, so if you take silicon carbide, we found that the electronegativity difference was just 0.7, and therefore the corresponding ionic character is just 12%. So it is very clear that the extent of ionicity, meaning this is 12% ionic and rest is covalent. So basically it's maybe 88% covalent and 12% ionic. So naturally this will have lesser resistance to heat, for instance, as compared to calcium fluoride or maybe aluminum oxide, right? So now we have been still talking about the attraction and forces of attraction and repulsion between the two neighboring atoms or two neighboring ions. Now let us see what inferences we can draw from this particular curve and what this curve essentially means. So we have seen that at the mean position the atom is most stable, and therefore when it deviates from the mean position, remaining at the same energy level, it will come back to its original mean position as seen over here. So dA and dB are two extreme positions from which it will come back to its original position dE. Now with increasing temperature, this mean position also shifts. That is because this curve is asymmetric about this vertical line. So naturally this will shift, and therefore you will see this macroscopically as thermal expansion of the metal, because in every atom there is going to be a shift in the mean position towards a higher interatomic separation. So the interatomic separation continues to increase with temperature, and as a result you will see macroscopically very a relatively larger dimension resulting from an increase in temperature. So it's like thermal expansion taking place. If it were fully symmetrical, if this curve were fully symmetrical like a V, then irrespective of the position or irrespective of the temperature, the mean position would have remained along a vertical line, and so on to the left and to the right you would have had symmetric move, meaning the two extreme positions would not have been different as the temperature increases. So the mean position wouldn't have shifted from the to the higher interatomic separation if it were a pure V. If the symmetry were there, then the locus of movement of the mean position would have been just vertical, and there would be no increase in interatomic separation. So naturally this radius of curvature, if it is sharp, it will mean that the Young's modulus is very high, because you have very small deformation that is possible for a given load. If this has a generous curvature for a given load, the displacement of the atom is much more, and therefore it means the Young's modulus is that much lower. So aluminum, for example, has got a relatively lower Young's modulus, so it will have something like curvature something like that, whereas steel or iron will have a curvature something like that, because it has got a much higher Young's modulus. High refractory materials, high melting point materials will have a depth of well which is something like that, as compared to relatively low melting point materials like magnesium, aluminum and so on, and zinc for that matter, which will have a relatively lower smaller depth of the well. So this the shape of this curve indicates many material properties. So we talked about the melting point, the coefficient of thermal expansion, and the radius of curvature relating to the Young's modulus. So when we talk about degree of ionicity, it also means that the bond is has two different characters partly ionic, partly covalent. So that is what is seen over here. In ceramics, you have wide range of ionicity because ceramics are made from a wide variety of materials having wide variety of differences between the ionicity of two participating elements. Semiconductors again have covalent and some ionic, so small amount of ionicity, and polymers are purely covalent. So most practically 100% covalent. So the degree of ionicity changes along this line over here between ceramics and polymers, and then you have ceramics and semiconductors having some amount of covalency, some amount of ionicity. So to sum up, the source of strength are different kinds of bonds in the material. The source of strength comes from the interatomic bonding. This interatomic bonding keeps these atoms together as a single aggregate. The interatomic spacing is governed by forces of attraction and repulsion between atoms and ions, because when I take a material, what I see as an aggregate is a collection of huge number of atoms, several millions of atoms, billions of atoms, trillions of atoms, which are spaced at a certain distance with respect to each other, determined by the distance determined by the forces of attraction and repulsion. And so I have this interatomic spacing leading to an equilibrium position of the atoms, and when I try to apply force on this aggregate, these atoms either try to come together or get pulled apart depending on whether it is tension or compression being applied. And then you have the so-called elastic deformation if the force is sufficiently small, because the atoms change their position, go away from the mean positions temporarily, and then come back to their mean position immediately as the load is released. So this is the source of elastic deformation as far as an aggregate goes. So we see the elastic deformation on macroscopic scale, whereas in case of individual atomic level, the change in the interatomic separation is virtually impossible to measure or extremely difficult to measure. Bond energies determine the melting points of materials. Bond energies also determine the mechanical behavior of the materials. Typically, if the bond energy is very high, the material is difficult to deform. It has got very high threshold load beyond which it becomes permanently deformed. So you can deform the material under elastic conditions to a large for a large load, and beyond that large load you can get some amount of permanent deformation. So materials, hard materials like tungsten, for example, have a very high yield point. They get converted from elasticity to plasticity at a much higher load because the bond energies are that much higher. The depth of the bond energy well is that much higher. So with this we come to the last part, that is the exercise, which I would leave it to you to work on as a homework. So we have the relationship between potential energy and the atomic separation here. There are two different materials which have got two different exponents n for this repulsive energy, and then you have two different values of A over here, and now you have to determine the interatomic spacing for these two materials and infer which of the two materials will have a higher melting point and a higher Young's modulus. So based on the shape of the curve, you will interpret that to have a higher Young's modulus and higher melting point. The third part will require a little bit more discussion on the arrangement of atoms, and therefore we will defer it for now, but then sections A and B can be done based on what we have discussed today. So with this, I come to the conclusion of today's class. Thank you very much.